Okay. So, last time, what were we talking about? We shifted coordinate systems. We've talked about using polar coordinates to integrate. And now today we're going to look at triple integrals after playing with double integrals for enough time. And then take a brief look at two very commonly used coordinate systems, which are spherical and cylindrical. Again, the idea is when things are round, it's easier to use these coordinate systems. They're not too bad, but they do require a little bit of kind of orienting yourself in a different way. So that'll come at the end. We'll take a little bit of time to just look at, what do equations look like in this space? What do, where do the points live and things like that? And then next time we're going to actually integrate in them. And so that's what's on Tuesday's lecture. Okay. Is integrating with spherical and cylindrical coordinate systems. So today the main focus is going to be triple integrals, using them to compute volume problems, mass problems. For those of us who are in the physics realm and chemistry and whatnot, these would be used for moment problems, momentum problems, things like this. But we really don't sadly have time this semester to get too much into those types of applications. But if you wanted to check those out in 15.4, they're really not beyond you. You could probably just kind of peek at the formulas, get a sense of what the story is behind them, and be able to tackle those. And my goal was with problem sets to actually do a little bit more of that, but I digress. We're going to play with volume problems, the definition of these things, and then how we can actually change the order of integration. We did that with Fubini's theorem, right? With the two variable double integrals. When you have three integrals, there become now six options, right? Because it's 3 times 2 times 1. So we're going to play with how you can change variables, and you kind of got to be careful about it, but sometimes it's advantageous to do so. So enough talking about what we're going to do, and let's just do it. All right. So first off, let's recall some helpful info. It's always a good idea. Remember that for an area problem from back when we were just pups, the integral from 0 to 10 of some f of x dx gave us the area under the curve of f of x. And we could have, now armed with our Calc 3 perspective, looked at this instead, and we've done this. Instead of that as be the integral from 0 to 10, and then the integral from 0 to f of x of just dy dx. Right, where this integral here, with some help from the fundamental theorem of calculus, right, is taken the place of that. So we got to swap out and say, well, this would be the area of a region where we're just integrating 1, and we integrate dy from 0 to f of x. So in this same vein, the idea was that we could swap this out. In the same vein, we've been playing with volume problems with double integration. We've been taking the integral from on this region R. F gives us the height, and then we have the area element. So we've got the height times the area, and that gives us the volume. But what if we swapped out that height in the same way and said this is, from some A to B and from some h1 of x to h2 of x. Let me give myself some space here. From some g1 of x comma y, or rather, let's write it like this. Getting ahead of myself. From 0 to some g of xy dz dy dx. And I seem to have switched variables. Hold on a moment here. Yeah, this up here should not be f. I didn't want to change the name of the function. That should be an f right here. So we see this. I'll highlight this guy. Let's just see the structure. So we replace this with this integral of dz in the same way we did before. And so we integrate 1 to get the volume. Instead of before we'd integrate 1 twice to get the area. Now we get volume. So in that same way, we can now integrate along all 3 axes to get volume. And then if we want to integrate over a space, over a 3D region, some function, all we need to do is input that function into the integrand, right? So this kind of stands in for the triple integral. We can throw a function in there, whether it be a density function or some other function in a higher dimension, right? It's talking about another output based on x, y, z that we can integrate over 3D regions. Okay, how we do that mechanically is a bit more involved than a double integral, but it works out to be a very similar process. So it should feel pretty familiar once we get going. So I'm going to sketch out kind of what's happening from a geometric perspective. So if we think about coordinate axes here, x, y, z. And let's say I've got some surface on the top. Something like this. Here's some g2 of xy defining some surface up top, and then beneath it it's enclosed by another surface here. We'll call this g1 of xy. So this guy's on top here. And so you can kind of imagine this blob floating in space above some region in the xy plane, like its shadow, right? So call this R down here. And R is a a type 1 region, because we can describe these boundaries up here as some y of x. Here's some h2 of x, and here's some other boundary over here, y equals h1 of x. So our R region, its shadow is trapped between 2 curves that depend on x. And then we know x starts here and stops here. So we'll call this A, x equals A and x equals B. And if your diagram's not as beautiful as mine, that's okay. You can just have this one. But the goal is to get you to see the different parts of the integral. If we're integrating 3 times, that means we need 3 sets of limits. So I need a start and stop for each of my variables, right? So I need, where do my heights, the z coordinates coming from the top and bottom of the surfaces, where do those come from? Well, we start down here and we stop up here. And then, all right, I got to scan across my y inputs. Well, if those are trapped between two curves in the xy plane, then we start down here and end up here. And then we can let x be two constants where we just scan from A to B. Okay, so top to bottom, side to side, side to side. But the way that we write this to give ourselves the most general form possible. So if we call this big thing up here S, the solid, say that the volume of S is equal to the integral from x equals A to B, from y equals h1 of x to h2 of x, and from z equals g1 of xy to g2 of xy. Now these could be constants, but they do need to be functions of x and y. So they can still be a constant function of x and y. Right? You can just do this with a cube or rectangular prism and just have it be perfect. But if you have curves or you have surfaces, then we'd write it like this, and it's dz, dy, dx. Again, starting on the innermost and working your way out. And I want to note here, too, that, and we'll do one example like this, you can switch the order by projecting differently. All right, so here I chose one that's kind of like the canonical example where we project over the xy plane. And so our region, our flat region is in xy, and our z is the height. But you could, define a surface based on equations of x, project into the yz plane, project into the xz plane, and we'll see how that happens. But this is probably the best way to illustrate it for the standard definition. So that's the volume, and so if we have a function defined on S, call it k of x, y, z, then the integral of this function where we use a volume element here, you notice this dv is equal to, and that's this piece up here that we just wrote, h1 of x to h2 of x, g1 of xy, g2 of xy, dz, dy, dx. So if you think of that function being density at any given point in the solid, and then we multiply that by the volume element as we go all the way around, scanning in all three dimensions, what are you going to get? You're going to get the total mass, right? If you have the mass per unit volume times the volume, that's what you're going to get. So a quick reflection on why the order dz, dy, dx, and why these limits of integration are where they are. Right. So in other words, why is it important that I let these limits here be functions of x and y? Might be a silly question. So the way to maybe think about it is, what if it wasn't, right? What if one of them had an expression of z? I integrated with respect to z first, and then I evaluate it add an expression with a z in it, and now that z is going to carry through the integral, right? And I'll have nothing to turn it into a value. When you take a definite integral, you should end up with a number, right? You should end up with a number, not a variable expression. So it needs to be a function of x and y, because those are my two remaining variables, right? And then at the very end, I should be dealing with constants, and in between, I should be feeding it a function of x if x is my last variable to integrate. Does that make sense? You want to make sure you're setting yourself up in that order. Again, we can change the order, but once you set it up, you have to carry it out that way. All right, so what I want to do, because there's a lot here, and these examples take a long time, I'm going to just compute one straight up with you guys so that we can get a feel for what this looks like when you compute them, so that if we need to bail on one of these examples, the approach is obviously the hardest part for almost all the problems you deal with now, right? So we want to go through the approach, and if we have to call off the integral, we'll do that. But I do want to go through a triple integral from start to finish just so you have that. Seems to be unbridled excitement about that possibility, so I'm glad. I'm very glad about that. So let's jump into it. Example 1, we'll just compute the triple integral. So triple integral, noting that, this variable goes with its corresponding exterior integral, right, as you move out. So this is really x equals 0 to 3. So we, partial integrate. We hold the other variables constant, integrate just with respect to x. So in that case, this whole thing's constant, and it's just a linear term, right? Y cos z to the fifth is just like the slope of the line. It's a constant number. So when we integrate this, we should just get x. So from 0 to 1 and from 0 to z squared, we get y cos z to the fifth times x from 3 to 0, dy dz. So what's nice is that all the lower limits are 0, so we don't really have to do too much computing. So what we'll do is we'll evaluate that at 3, and I'm actually just going to pull the 3 outside, and so we're just going to be left with, again, y cos z to the fifth dy dx. dy dz, dy dz. Right, should be no more x's now that we've integrated that. So now integrating this with respect to y, well, with respect to y, cosine of z to the fifth is constant. So similarly, this is a line that must have been the derivative of parabola, so we just go 1/2. So we get 3/2 out front, y squared cos z to the fifth from z squared to 0 dz. And then we will plug in the z squared into y squared, getting z to the fourth. So get 3/2 z fourth cos z to the fifth dz, which is good because we needed this in order to do this integral, right? We need that fourth power. So we really need a 5 in here. So bring out a 1/5 to the outside. So we can integrate, and we should be left with, what, 3/10 sine z to the fifth from 1 to 0. Sine of 0 is 0, so this is really 3 sine of 1 all over 10. Whatever the sine of 1 is, they never make you memorize that. But that's the feel of it. It should be, once you take care of the first one, now it's just a double integral. Right? That's how these go. So really not too shocking. In some ways I kind of feel bad, like it should be more intense than that. Right? It's a triple integral, but really it is kind of an iteration of the same thing that we've been doing. So it's not too crazy. So we're going to do a volume problem now. I'm going to give you the general kind of algorithmic way to think about doing these. It's not going to fit every problem, but it'll be a good starter, a good kind of general strategy. That's a better way to put it, on how to tackle problems like this. Any questions on just the computation before we move on? I want to make sure we're hanging with the algebra. Okay. Awesome. Find the volume of the region E, which is enclosed by z equals x squared plus 3y squared, and z equals 8 minus x squared minus y squared. So it's not necessary to know what these things look like, but it can be very helpful to have a general idea of what they look like. So what we're going to do is we're going to compute the volume of this thing. And the hardest part of this is finding the limits of integration. Okay. So we're going to spend most of our time talking about that. But we know that the volume of E is given by the triple integral over E of, we're going to say dz, dy, dx. So we know this is equal to integral a to b from some h1 of x to h2 of x, and from some g1 of xy to g2 of xy of dz, dy, dx. So really we're on the hunt for these things. The inequalities can help to see them in this way too. So we're looking for all these. So I was saying before, it can help to know what these things look like, or you can throw them into a visualizer like CalcPlot 3D, GeoGebra, to take a look. But when we're given it in this way, where it's enclosed by two surfaces of z or functions of x, y, we should probably use that to our advantage. So we've got a surface on the bottom, a surface on the top. It might not be clear which one is which. So what we can do, though, is find that curve of intersection. If this thing's enclosed by these two surfaces, they're going to intersect. And so we'll set them equal. The idea that this boundary will give us a projection for our region R in the xy plane. So the curve of intersection here is, if we set them equal, so we get x squared plus 3y squared equals 8 minus x squared minus y squared. Set the z's equal. And we solve for an equation here, so we get 2x squared plus 4y squared equals 8, which we can really divide everything by 2, make life a little bit easier. We know, especially because of this equation over here, that our z is positive values only. Right, the x squared plus 3 squared y is like a elliptic paraboloid. It's facing upward, right? It's like a bowl. So we're really only talking about z values that are positive here. And so what we get is a projection of this ellipse, x squared plus 2y squared equals 4. So we're going to use that in a little bit. When we look downward from the z-axis, parallel to the z-axis, this is what we'll see as the projection of where these two curves intersect. They intersect in this ellipse. All right, so we'll store that for later. And how we typically set this up, if we're doing it in this order, z, y, x, then that's the order in which we want to find these limits. Tends to make it easier. Doesn't always work that way. So find the z limits first. One way to do this, if you have a graph, and I'll sketch out what this looks like in a moment, is you can take a typical xy in the region R, shoot up a line through the surfaces. So if maybe I'll cheat a little bit, grab this. What I mean by that is to take, why didn't that work? Take some point x, y, 0, shoot it up, call it M, whatever you want. And where it enters and leaves, that's your inequality for Z. Right? It hits the bottom surface and pokes out through the top. Those are your limits of integration for Z. Because this should be a surface of xy. All right, so here's your g1 of x comma y. And here's your g2 of x comma y. So you can think the exit and the enter. Drag these down here. What is happening? I'll deal with that. So for us, what you can do is, if you don't have a good visual sense of this in your head or sketched out, pick a point that's in the region R. So since we know this region R is this ellipse, you know the origin's included here, right? That's a nice easy point. So you could think about taking a point in the origin. So this thing's what? We divide everything by 4. Longer in the x direction. So imagine taking this and shooting the point straight through. What are you going to hit first between these two? Let me just draw in what these are. Plus 3y squared, right? So if I plug in 0 for x and y, because I'm at the origin, we see that the higher one is this guy, because it takes on a value of 8, right? Whereas down here, this guy's a z value of 0. I'm using my pen to point, but this is higher because z of 0, 0 is 8. Here, z of 0, 0 is 0. So I know that this one's the bottom one, right? I'm sending one test balloon through and see which one do you hit first. So I know now that this is my lower surface, this is my higher surface. So for my z limits, then, and I'm really making a great, like, normally you would just see, oh, these are solved for z. I'm going to figure out which one's lower, and then those are my limits. I'm making a great deal about it because I'm trying to illustrate what's going on. So our limits for z are x squared plus 3y squared up to 8 minus x squared minus y squared. You can see how these are functions of x and y. That's what we wanted. So now for my y limits. Remember, we want some functions of x. They could be constant or they could be formulas involving x. So another nice way to think about this, if I take some, so if M was like my test balloon, if I shoot out a line parallel to the y-axis, the one I'm caring about right now, I'll call this L. It's in the xy plane. This is going to also enter and exit a region, and that region is R. And that's going to tell you your inequalities for y. Okay. So here's my enter and exit. I know this diagram's getting a little busy, but what you do is you deal with your projection now, and you say, right, I've got a ellipse. I draw a line crossing through this thing. It's going to enter down here and exit up here. And really we can take that from our solution up here. There's a way to get around doing any of this geometric stuff, and that's just solving for y, testing out some points, right? So go ahead and solve for y as a function of x. You get what? 4 minus x squared all over 2. Let me take the square roots of plus or minus square root 4 minus x squared over 2. And so obviously these are two semi-ellipses, right? The negative ones on the bottom, positive ones on top. So that tells me that y is between these two guys. Which is what I wanted, right? I wanted functions of x, and I got them. So here's my y limits. And the goal is in doing this work of figuring out those functions for z and then y to integrate over is that our last one should be constants, right? So our x limits, then you can go to your projection and just see, oh, well, they go between what? Well, when y is 0, they bounce between -2 to 2. Does that make sense? Okay. All right, so we've got z limits, y limits, x limits. That's the hardest part of these problems, okay, is doing just what we did. The actual integration is, there's going to be really not too much new, maybe some combinations of things in ways you haven't seen them, but not too bad. So then the volume of, what do we call it? S or E? Called it E? -2 to 2. From negative square root 4 minus x squared over 2 to positive 4 minus x squared over 2. And from x plus 3y squared to 8 minus x squared minus y squared. dz, dy, dx. So we're going to just carry this out 2 steps. I'll get it to a double integral, and then we can just kind of wave it on from there. So if we're just integrating dz, then what we really get is z evaluated between the top and the bottom. So this really just becomes 8 minus x squared minus y squared minus x plus 3y squared dy dx. Clean this up here. So this should be x squared plus, right? Yeah, I dropped an exponent there. Slow it down. So negative x squared minus x squared, and we got a negative x squared minus 3y squared, so we get 8 minus 2x squared minus 4y squared dy dx. Then you'll integrate and you'll get, a factor of y here, here, and then this will become y cubed. You'll have some radicals to deal with, and that's where we're going to call it because we're not gonna crunch through that. I mean, it is what it is, but I want to illustrate more examples for you guys the best that we can. So you got this. But once it's a double integral, everything carries out exactly the same. Obviously, the hard part, setting these things up. So questions about any of this approach here? All right, so I do want to let me give you like a better visual of what we're looking at here. I'll let you finish writing this up. Has anybody used this MathCha editor yet? You played with this? A little bit? Let's see, this is 15.6. All right, so here is what we just worked on. So I'll give you a moment to kind of parse through it and line it up with what we were just doing. Right, our region here was that intersection, the projection of that intersecting curve down was that ellipse. The top surface, the bottom surface. And then shooting that line M from a typical point through, seeing where it enters and leaves. That's how we're going to find out what our Z limits are. And then for our Y limits, send a line down the Y axis in the XY plane. See where it enters and leaves the region. That gives you a function of X. And then X is what that L line scans through, right? If it like spans through down the x-axis, what's its start and stop point? Well, it's -2 and 2. All right, so I'll drop that in the notes as well. Okay. I got a question about the next test. I will answer that at the end. Just remind me about that. And we'll shoot back to here. Okay. All right. Swapping the order of integration is another skill from this section. So sometimes it's advantageous to swap the order. We just want to look at it from a different perspective. Whatever the reason might be, it is possible to do, and there's a lot more ways that you can swap the order now that we've added a dimension, right? It becomes 6 different ways that you could write this. So given this integral, 0 to 1, 0 to x squared, and from 0 to y, some function dz, dy, dx. We want to write as a triple integral and reorder to dx, dz, dy. Again, you can probably see already why we need to worry about this, because the way we feed it the functions of the variables that we have left, right? And at the end, we shouldn't have any variables left. So we can't just simply swap them around. We have to take some care and see what are the limits when we integrate in this way, when we scan across the axes in this order. All right, so we can say that this is equal to some triple integral E dv, where E is some region of points x, y, z where what is happening? Well, we can think about these things separately and then all together. So we see that z is spanning between 0 and y. So we could think about this being, all right, z is bound between planes z equals 0 and z equals y. This is technically a, function of x, y. And then y is a function of x is our next one. We see that, y varies between y equals 0 and y equals x squared. And x we see is just bound between 0 and 1. So it still might be hard to picture this, and this is actually not super easy to visualize in your head. But what we can do is let's map out the different projections. So what we'll call, R1 is the projection to the xy plane, the shadow of this thing in the xy plane. Well, we know this is the set of points xy, where what? Well, x is bound between 0 and 1, and y is bound between 0 and x squared. So what does that look like? Well, in the xy plane, y is bound between 0, which is the x-axis, and then the parabola y equals x squared, so something like this. And then here's x equals 1. So really here's my region here. Another way to, here's x equals 1. Another way to think about this would be a set of points where if we solve this for x, because we're in the positive quadrant here, we can say, well, really, this is where y ranges between 0 and 1. And that x is between the square root of y and 1. All right, all my x values, if I go, if I slice in this direction, I'm going to hit here and leave here, which is x equals square root of y. Why is this happening? So it's two ways to think about this projection. And then from there, you can take, like I said, that test balloon, that line M that shoots perpendicular out of the region R, hitting the surface. Hopefully in two spots, you'll have an enter and exit, and be able to grab those limits. Another way we could write this, because we want to go dz or dx dz dy. So the other way we could think about this is the yz plane projection. And so we know this is going to be the set of points yz where, well, we're going to have to do a little bit of work here. We know z is bound between 0 and y for its values. And then what is y bound by? Well, we're going to need to look to the other equations here and see that y is bound between 0 and x squared maxes out at 1, right? So we know that y2 is sandwiched between 0 and 1. So what does this region look like? Well, here's yz. Y ranges between 0 and 1. Z goes between 0 and z equals y. Well, what is z equals y? It's a plane, so in the plane it looks like a line, z equals y. And we're talking about z values less than this, so it's really this triangle over here. All right, so that's the shadow of E in the YZ plane. So again, you could take a point, send out a balloon, and hopefully you can find your way. And the last way to view this is in the XZ plane projection. And so what is R3? Well, it's just points XZ, where we know X is bound between 0 and 1. And we said that Z varies between 0 and Y. Well, Y is 0 here, so we need to be in terms of X. Well, Y is varying between 0 and X squared. So we know that Z is bound between 0 and X squared. Again, you'd want one of these to be constant and one to be in terms of just the other variable in the plane, right? Does that make sense? Okay. So what does this thing look like? XZ projection between 0 and z equals x squared. Z equals x squared is a parabola. X is between 0 and 1. So again, it's this kind of crescent shape guy over here. So this is really just to explore the different ways you can switch it up. We were tasked with writing and dx dz dy. So what does that mean? That means I'm going to actually back this up and give myself some more space here because these are way more involved. So that means we're going with respect to x first, then z, then y. So that means we're sitting over the yz plane, right? And shooting a test balloon through there. So we're over the yz projection here. So that means y varies between 0 and 1. Z varies between 0 and y. And then we're going to need our x limits that are in terms of y and z. So what is that? Well, we know x varies between radical y and 1. In terms of, wait, hold on. Yeah. So x is above radical y. And maxes out at 1. It's kind of blurring together. dx, dz, dy. Yeah, good. Okay. Questions here? It's going to take some playing with and some getting used to. The change of coordinates stuff in particular. But we are going to, we might have time for one more here. Let me see what we've got. One moment. I had an if time example picked out, and it disappeared on me. All right, let's do this. Do a quick application problem. So an average value of a function in space. You might remember that the average value of some function f was given by, in 1D, the length of the interval dividing the single integral. And for a double integral, we said we divide by the area of R to get that weighted average. So divide by the length in 1D, right? Divide by the area in 2D. Guys are next level with your averages. I get a lot of questions on, you know, what is my grade point average? And it's just you have, 12 grades a semester. This is a lot more intense than calculating that on your own. But anyway, for 3D, what are we going to do? We're going to divide by the volume element, right? Because that's what we're carrying along with the weight as we go around. So then we're going to divide that out, and then we'll get the average at the end. Okay, so average value of a function in space. So big F average on a region D is 1 over a volume, or region E. We'll stick with that. So we'll just jump right into an example with this, because I feel like intuitively this makes a lot of sense. So just being able to do it would be nice. All right, so we'll take the product of the coordinates as we bounce around a cube. Bounded by the coordinate planes and the planes x equals 2, y equals 2, z equals 2 in the first octant. So, you might be able to figure out what the limits of integration are just by holding this in your head. It's not too bad, but might be worth a quick sketch. We're in octant 1 after all, so it's not too terrible. Talking about the planes, x equals 2, y equals 2, z equals 2, so we do end up generating a box. So you can go through that same process, but I think we could kind of fast track through that, and we just know we're integrating from 0 to 2 on all the coordinate axes, right? Pretty nice. Sometimes rectangular coordinate system is nice. This is one of those times. So average value is 1 over the volume of E times the triple integral over E of big F dV. So, we could compute this using a triple integral, but we know that this is a cube. So let's just use that fact that this is a cube. And so its length, width, and height is 8. All right, so we know this is really 1/8 times the triple integral. If you didn't have that, what could you do? Well, you could just take the triple integral over the region without the f, right? You just do it with the volume element, and then that will give you the volume of E. But in this case, we knew it, so we're able to just write that in. So now we'll take the triple integral over this region E. We know our limits of integration, so that's really nice. So this is big F average is 1/8 times the triple integral of big F, which we said is the product just x, y, z. dz dy dx. Really doesn't matter which way we go first on this one. So integrate with respect to z first, so we'll get a half, so I'll drop that out to a 16th x, y, z squared from 2 to 0. So that's 4. So 1/16. We'll bring the 4 out and worry about it later. And same thing's going to happen here. We integrate with respect to y. So we get 1/4 x y squared over 2. So this becomes 8 from 2 to 0 dx. Which, again, that's 4 to 0. So we bring that 4 out. We get a half. 0 to 2 x dx. So it's a quarter times that whole thing again. It's 4. So that gives us 1. Okay. So average value of the product of all the coordinates in that cube is 1, which is pretty interesting. But just a nice way to be introduced to the idea of the average value. Again, your region could be a lot more interesting, right? The constraints of the variables you're actually working with, whether it be a social science experiment or a physical body, whatever it is. And then, what's the average value of the velocity of this thing, the charge in the system, whatever it might be. So that's average value. Lastly, what we're going to do, because you guys are going to have, just like everything in this course, the practice, the real familiarity comes from the practice problems. So you'll have some practice problems with triple integrals. I need to introduce these 2 new coordinate systems before we can start doing triple integrals in those spaces, which is what we'll be doing next time. And so we will jump into that now. So we're going to look at cylindrical coordinates first, because it's a natural extension of polar, and then spherical coordinates. All right. So kind of shifting gears here a little bit. Okay. So what I want you to do is think for a second, because I think you can get a good intuitive feel for this. People don't like trig, so that can be cumbersome, and we can get lost in the notation. So you can get an intuitive sense, right? We said at the beginning of the semester with the rectangular system, there's your wall in your room can kind of serve as like the XZ plane, the YZ plane, and then the XY plane, right, with the floor. The seams of that are the coordinate axes. And you can even think, from your own perspective. Now, you sitting in your chair, right? If you maybe make a 90 degree angle between your 2 arms reaching out like this, that, your left arm is the y-axis, your right arm is the x-axis, and then you're the z-axis, right? Your head looking straight up. So, anything in your room, you can use yourself as a measuring stick, of how far over, how far up, right? How far out, how far over, how far up or down. And so in the same way, we can morph the way that we do that same thing, that same mapping of where stuff is, to, instead of over, over, up, it can be, right, radius out, angle over, and then up or down, right? Straight up or down. So that's what cylindrical coordinates are doing. It's, instead of, how far over, how far up, it's how far do I swivel my chair, that's theta, right, my angle, radius is how far away in a direct line from me to that thing, and then how far up or down is it in space vertically on the z-axis. Does that make sense? So everything's in reference to like this imaginary cylinder of spinning, how far the radius is, and then just up and down. So they're of the form of triples. So you still need three parameters, r, theta, z. We know that r, theta are the polar coordinates. Z is the height. Regular, rectangular height. So the same mappings work, which is really nice from what we remember. So some equations here to convert. We know that x is r cos theta. We know that y is r sine theta. This is my favorite one that we write down. Z equals z. Nice. Awesome. We've got r squared equals x squared plus y squared. And another nice one to have in the back pocket is that the tangent is the slope y over x. It's the ratio of y to x. Okay, so these are good ones to remember. Park these in your memory too. That's going to be helpful later when we get to spherical because it can seem a little bit much. But x is r cos theta, y is r sine theta. So when things are circular, cylindrical, this is really nice. So I'm going to sketch a picture. And again, you're welcome to draw along, but not necessary. You can just kind of follow. So what you can think about is a cylinder in 3 space. And so we'll take a given point here. Call this P, which is r theta. We'll fix the values. We'll say at a radius a, at theta naught, and at height z naught. So what does it mean to be this little point? Well, it means that it's resting on, this plane. Here's z equals z naught. Here's that height z naught. So it's resting in that flat plane vertically. Let me draw that a little bit better. The projection down into the xy, and we see here this radius that meets it outward. This angle that's turned from the positive x-axis to this point, that's theta. Theta naught. And what that actually does is it forms a plane parallel to the z-axis. And then this cylinder, where it's resting on the edge of, this is of radius a. Okay, so it's on the edge of this. Or it should be solid on the outside here. It's on the edge of this cylinder, the intersection of the plane z equals z naught the plane theta equals theta naught, which is how far we're spinning around the z-axis, and then how far out, that radius in the xy plane. Okay, so here's r equals a. Another simpler way to draw this, because it's kind of busy with all the dotted lines and stuff, is like this. If I've got some point P, it is like this, the theta this distance is z, and then this length from here to here, that's r. Does that make sense? Okay. So we'll think through what surfaces and some equations look like here. So just, I don't know, we'll phrase this as like questions. 1, 2, 3 in the rectangular goes to what in polar. So point 1, 2, 3 out 1 over 2 up 3. How would we represent this in polar coordinates? Well, what do we need? We need the z height. Well, z is just the same z height, right? That's the how high up you are along the axis. So we know that one. That's just 3, because z equals z. X and y, what are the mappings in the polar? R cos and R sine, right? Radius times angle. So R cos theta and R sine theta. Well, what's R, what's theta, right? Don't know. We got to draw a triangle, figure it out, right? So what do we have here? Draw out the radial arm. Well, the length of this thing is r, and the length of this thing is 1 plus 4, which is radical 5. Right, because it's really just a 1 plus 2 over here. What was I going to say? Oh, then theta. Right, what is this angle here? Well, theta we're going to have to figure out from, I mean, we could use this triangle that we have. You could use this triangle over here, because you know that you've got 2 and 1 here, so you could use arctangent. It's typically the best one to use for this, right? Why is arctan the best? Well, arctan of y over x gives us theta. So arctan of our y is 2. And so that should give us what here? .11 radians. So that's what we've got for these two guys. So our cosine, let me drop this down, make this a little bit bigger. Radical 5 sine of 1.113. Now you could just get a decimal value for these, but that's no fun, So that's good to go. And yeah, that's good enough. I mean, you can, you've played with this in 2D, so it's really just adding z. You've done this enough. So I want to talk about what surfaces and equations look like. I think that's a little bit more important. So 2, what does r equal 2 sine theta look like? Well, what does it look like in the polar plane, the r theta plane? R equals 2 sine theta. Well, it looks like this. It's a circle, right? Circle of radius 2 up here, and so that's its cross section. And so it's really, this is a slice and it's a cylinder going straight up and down parallel to the y, or to the z-axis, right? Parallel to the z-axis. Think about it again like this here. You see r and theta, so this tells you that z varies. Right? So whatever this shape is on its own, z varies freely, so that's the up and down dimension. Right? So take this thing and send it up and down. All right, how about z equals 5r? So z equals 5r, what does that look like? Well, if you slapped a projection into the, let's see, the YZ plane, z equals 5r is like a line out like this way, right? And so, and it's got a slope of 5. And so, or not, yeah. So it's pretty steep based on the radius, how far out you are, right? R, it's 5 times that height upward, right? But we see z and r, so we don't see theta. So what does that mean? That means theta varies freely. So this thing spins around the z-axis, and we get the cone, right? Upside down party hat. So it's z and r, and just seeing z or just seeing theta, theta equals a constant, you're going to get a plane with that. So you have a couple, just a few practice problems on cylindrical, orienting yourself in that space for tonight. And the same with the upcoming spherical coordinates, which are a little bit more involved. So I think we should jump into them right now. Questions on cylindrical, though? Okay. You might be asking yourself, why are we talking about this? Triple integrals are tough. They're a lot tougher than double integrals or single integrals. So whatever we can do to simplify them, we're going to do that. And so if the region is cylindrical or friendly in terms of polar coordinates, we're going to do that. It will frequently be the case. We might be looking at a cone, looking at an elliptical surface. If you have an ellipse, and I think you had a practice problem where you did this, you can easily take an ellipse to a circle, and then a circle becomes an easy polar equation, and then you're good to go, right? So it's a good tool to have in the bag of clubs. That's not a metaphor, but I'm just making them up, That's fine. So let's scoot into spherical. It relies on some stuff from polar, but it is profoundly different. And what's even better is that there's no consensus on it in the math community. About half the books use one notation and half use the other. So enjoy being confused when you look stuff up. I'm hoping that telling you ahead of time will front load you with this information. You won't be confused. But let's look at spherical coordinates. And I'm going to arm you again, like I did before, with an intuitive kind of explanation. But they're of the form of triples. The point is given by rho, which is like a little P-looking guy, theta, and phi. So theta is the theta we like. So that's good. We already know theta. We got to figure out what's rho, what's phi. So back to being in your chair for a second. All right, think about the space that you're in. And so now we can visualize a different way to orient ourselves, which is, pick a thing in the room that you can look at for a second. And now think about in terms of, again, spinning your chair, that angle to point yourself toward it. That's theta. And then rho is the radial distance from the origin. So you, like whether that be your belly or your eyeballs, whatever you're choosing as the origin, that's the radial distance from the origin to the thing, to the point in space. And then rho, instead of being a z height, it's the head nod up or down. Okay, so it's the angle that you make with the vertical axis. That's phi. And what phi does, just like your head, it only goes between 0 and 180, right? This is like upright. You're completely parallel with the z-axis. And then there's like looking down. Okay? So, or you could think about starting looking straight up. And then how far do I need to look down to get there, right? So there's spinning around. You're going to look like a crazy person if you're doing what I'm doing. Spinning around, and then how far do I look down? And then how far out from the origin as a radius from like a sphere. Okay? Not r in the plane, but r in terms of a spherical radius. Okay, so that distance to wherever you are in the space. So rho is a little bit more involved than r in that way. But when things are spherical or conic, this is a really nice way to go. So let's jot these down. So what is rho? Rho is the distance from origin to the point, or from the point to the origin. Theta is the theta from cylindrical. It's that rotation about the z-axis. It's theta. And then phi is the angle that the position vector makes with the vertical axis. It's the head nod. All right, how far down do I have to look? And phi ranges from 0 to pi. All right, so some helpful equations, and then we'll sketch out how things look. Actually, let's do the sketch first. So let's start with a point P out here. Rho, theta, phi. The consensus thing too, by the way, it's not a huge deal, but it's just what theta and phi order are in. And some people even make theta the vertical angle, which switches it up from the cylindrical, right? So that makes it even more confusing. So just be aware of what angle you're talking about in a given moment, because one goes from 0 to 2 pi, it's the spin around the axis, and the other is just from top to bottom. So from here to here, let's do this. So imagine if this was a sphere centered at the origin, and this length here is rho. The yeah, let's do that. The tilt down. So this vector OP, this angle that it forms with the positive z-axis, we're calling this phi. And if we fix that phi, what it does is it forms a cone that goes around this sphere. Think of it there, or you can think of it down here, whatever. But it forms this cone. If you fix phi and let rho and theta vary, it's just all the points that are on this cone. So that's rho outward, spherical distance out, emanating from the start of the sphere to wherever it is, how far down or up from the vertical axis is phi, and then how far do I spin around my vertical axis this way? That's theta. And again, it kind of forms a here we say it forms a half plane because rho shoots outward, right, in one direction from 0 to the point. So we say this gives us a half plane hinged at the z-axis, hinged in the chair. Theta gives you that half plane. So again, kind of a busy picture. I'm going to try to do a more simplified one down below. But let's get some equations going to convert between what we know and this new system. So actually, it might help to have this second diagram. Let's just do that. It is fine to just memorize this or to have it handy, but it's nice to know where this stuff comes from. And you should be at least somewhat curious, damn it. You know, should be into this stuff. So here, theta spins from the x-axis to the point P. So that's my theta here. This height, actually move to, this height is z. Now on this projection out here, you can see we still have like an x distance and a y distance. Rho, we said, is this length, and it's really the hypotenuse of this triangle. And phi is this angle here. So, a couple things I need you to see here. First is that, what is r? Well, r from polar, if you remember, is this distance out in the xy plane, in the polar plane, right, on the cylinder. And that's going to generate some stuff for us. Since r is this guy here, if you think about it in this way, for phi up here, the sine of phi is this length here, right? Because it's the opposite over adjacent, or opposite over hypotenuse, rather. Opposite over hypotenuse. And what's our hypotenuse? It is rho. So this guy, r, is really rho sine of phi. So why that is helpful is because we know that x is really r cos theta, which tells us that x is really rho sine phi cos theta, if that's r. And likewise, y is r sine theta, so y is really rho sine phi sine theta. Okay, so sine of the angle dropping down and sine of the angle turning around. And so what's z? Well, if r was given on this side, z is this side of the triangle, so that's the cosine of that angle phi. So that's rho cos of phi, because that's adjacent over the hypotenuse, right? And then what is rho? We said rho is the distance to the point. So if you have the xyz coordinates, it's really that just Euclidean distance, which we could also say is r squared plus z squared. So why is this nice? Well, let's think about some equations, some surfaces, etc. You know, rho squared equals 4. What does this thing look like? Well, we think about it like this, it's radical x squared plus y squared plus z squared equals 4, which is really a sphere of radius 2. Right? So we can write it like this instead of like this. That's much better. It's much better to deal with. So things that are conical, things that are spherical, rho reduces all of that. So that's pretty nice. Now we have access to all the trig identities from sine and cosine. Those are like the building blocks of things that spin. It's awesome. So let's do one quick example here, and then we'll call it. Represent this in spherical. So we've got x squared plus y squared plus z minus 1 squared equals 1. So you probably have a guess that this is a sphere that's been, its center's been shifted up 1 vertically, right? So how do we represent that with spherical coordinates? Well, we can plug in what we know for x, y, and z and see what happens. So x is rho sine phi cos theta, cos squared theta. No, rho sine phi cos theta, but it is squared. Y we said is rho sine phi sine theta squared. Plus z we said was rho cos phi. And so what's nice, all these things get squared, which means we're going to get to apply the Pythagorean identity. What do we get? P squared cos squared phi minus 2 rho cos phi plus 1 equals 1. So what happens here? Well, these have a common factor of this guy, and they're distributed to cos squared plus sine squared. So this is just 1 times this. So we get rho squared sine squared phi plus rho squared cos squared phi minus 2 rho cos phi. I'll subtract 1 from both sides. This is equal to 0. Similarly here we got Pythagorean identity, so we factor that out. We just get a rho squared minus 2 rho cos phi equals 0. And so, I mean, you can add this to the other side, divide both sides by p, and what do you get? 2 cos phi to describe the whole surface. Not too bad. And actually might take some playing with. I think by removing that last one, by dividing by p, we got rid of the negative side. So you might actually, this is just half of the sphere. So I might need to stick with this one. Because phi only ranges from 0 to 180, right? But if it's 2, maybe it's double it. I'll have to look at it. But that is, yeah, those are the examples I wanted to do. We are at the buzzer, so I want to be respectful of your time. But any last questions on this stuff? Are you feeling disoriented yet? Got 3 ways to navigate 3D space now. There are such things as elliptical coordinates too. We're not going to cover those in this class, but there's probably a bunch more. All right, you look excited. I'll let you get after it. If you have questions, you can hang out. Otherwise, we'll see you next time.